Good afternoon, students. So, we will start our discussion on the structure of the MOSFET and second order effects. So, let us have a quick recap of what we discussed last day. So, then we will continue on our discussions on different second order effects and following the discussion on MOS capacitance and other topics. So, last day we discussed about the how to derive the current equations, and what we have derived. We have derived the complete current expressions for I d is equal to mu n C x W by L V G S minus V T H, which is known as the overdrive voltage, into V D S minus half V D S square, right. So, this is your complete equation. So, in these equations you can put three conditions, right. One is for cutoff, V G S is less than V T H, your I D is equal to 0. Another is V D S is less than V G S minus V T H, that is linear region. So, this is your complete linear expression, and if V D S is much less than this, these terms you can neglect, right. And then third is when in saturation region, when V D S is greater than V O V, you can have half and square, right, half mu n C x W by L V G S minus V T H whole square. So, that was your equation at saturation. So, that we discussed, and in addition to this, what we discussed last day, that what is backgate effect, right. If you see the expression for the threshold voltage, it is having three component. One is your work function difference between the poly and the substrate, that is this is the work function difference. Second component is your Fermi level, and third component is the, because of the capacitance form here, this oxide capacitance. So, you know Q is equal to C V. So, from this the capacitor, if some charge is deposited, it will V is equal to Q by C. So, if some charge is deposited on the capacitance, some voltage will be formed, right, voltage will be accumulated. So, as in this depletion region or space charge region, some charge is deposited. So, accordingly another voltage component will be built up, right. So, if you take these three component, that will define your threshold voltage. Okay. So, this is our threshold voltage. When your V G S will just cross this V T H, then what will happen, your channel will start to invert. So, what is the meaning? Originally your substrate was P, now what will happen, some electron will come out and make a channel, right, and you will, if you add a positive drain voltage, you will get a channel current. So, that we discussed last day. And what was our backgate effect? Backgate effect was that if we add some positive VSB, what will happen? This VSB will help to increase the threshold voltage. Okay. So, we discussed this last day, right. So, what was happening actually, because of this VSB, this compared to this, in this case the depletion, the charge stored in the depletion layer is increased, right. This voltage helps to increase the depletion width or the charge, this Q depletion, hence the VTH is little bit increased, right. So, that was the, so because of this effect, this is the backgate coefficient gamma, and that depends on the epsilon silicon twice Q, substrate doping and the COX. Channel length modulation we also discussed. Because of the punch through effect, if we increase our VDS and if this VDS is more than the overdrive voltage, then what will happen, this channel which was just tapered and ending at the drain terminal, it will move away, right, because this voltage is, this field is increasing, and as a result what is happening, our effective length is decreasing, and which will increase our current. Okay. So, this is modeled as this is indirectly, this effect is indirectly depending on the VDS. So, we have considered one channel length modulation effect coefficient lambda, and we have multiplied this ID with 1 plus lambda VDS. So, this is our channel length modulation effect, and ideally when if it was flat, our resistance at saturation was infinite, right. Now, we will be having a finite impedance at saturation. So, next second order effect is subthreshold conduction. So, we considered that when VGS is greater than VTH, the channel starts to conduct. So, as if we assume that at VTH the current abruptly goes to 0, is not it? We were considering like as if at VTH it is just instantly going to 0, but in reality it is not happening, right. If you enlarge this, you will see that it is not instantly go to 0, but it will take a exponential form to go to 0, right. So, even when my voltage is below VTH, that we can say that it is in subthreshold region, right. Below threshold means subthreshold. So, originally for ease of expression, we assume that it turns on above VTH, okay. But in reality even below VTH it is in weak inversion. Above VTH it is in inversion, but it is not that that inversion layer was not building up, okay. Even below subthreshold region, below threshold voltage region, there is a weak inversion region, and it takes a time to go the current to 0, okay. So, this slope is generally we call it like a slope factor or S. We denote this slope as S, and this S is important in case of digital design and to determine the performance of the device. If some new device is formed, they want to see that what is its subthreshold slope. Okay. For example, in this case say S is equal to 80 millivolt per decade. What is the meaning? Suppose current is falling, right, here the current is in log scale. So, 10 times it is falling, so it is decade. So, how much voltage the VGS should decrease how much millivolt, so that current should fall by 10 times, right. So, it takes 80 millivolt to drop, the voltage should drop 80 millivolt, so that current drops by 10 times. So, its slope is 80 millivolt per decade, and this slope is denoted by capital S. Okay. So, this is our exponential expression of the current in subthreshold region, and this is the expression for the S. Okay. So, now you see in S there are two term, one is N, that is some empirical value, and there is a thermal voltage KT by Q, that is a constant, you know, roughly at room temperature 25 millivolt, and ln 10. Now, in digital logic circuit you can understand that digital logic circuit, the transistor is operating as a switch, right, it is on and off. So, when it is going off, you want it to go off quickly, right. To make it an efficient switch, when it is going off, you would like to it turn off quickly. So, if you want it to turn off quickly, what value of S you should you will desire, larger values of S or lower values of S, so that it turns off quickly? It should be lower, right. So, if S is lower, that means less voltage drop, it current drops quickly. So, you see now in this expression, if you put n is equal to 1, that is the sharpest roll off possible in case of MOSFET. Okay. If you put n is equal to 1, this n is some empirical parameters for calculations. So, you will get 60 millivolt per decade. Okay. Generally for MOSFET this n is little bit larger than 1. So, if your n is equal to 1.5, you get 90 millivolt per decade. Okay. So, this n, the value of n depends on the intrinsic device topology and its structure. So, in case of MOSFET, you are bounded by 60 millivolt per decade. Okay. You cannot go below that. So, if you want to decrease the subthreshold leakage, or if you want to suppose for low power, sometimes designer what they do, they intentionally work on in the subthreshold region. Okay. In subthreshold region your speed is slow, but power is also slow. Now, in subthreshold region your leakage is more important, right. So, if you want to have slope, the subthreshold slope less than 60 millivolt, you need to explore different architecture, different device structure, for example like silicon on insulator or FinFET. Okay. For MOSFET we are bounded by this 60 millivolt per decade. Next second order effect is velocity saturation. Now, we consider that our mobility is constant. In this case, if you see, this is our velocity, this is our electric field, and this mobility, this slope is known as the mobility mu. This is constant in this case, this slope is constant. But at higher electric field what happens, that because of the, if you increase your electric field, then what will happen, the speed will increase, scattering will be also increased, and because of the scattering, although we expect that we have increased the field, so velocity should be also increased. Here the velocity is constant, but suddenly what is happening, that instead of a constant velocity, the velocity start to decrease and it gets constant. Why that happens? Because of the scattering. All the majority this electron, they scattered with each other device structure, and the velocity that drops and gets saturated. Okay. So, because of this effect, we see that in long channel devices, in the saturation region our current was constant, right. But the same effect, if you consider a long channel device and a short channel device, you will see that saturation of the velocity is happening quite early. Okay. Because in short channel effect, what is your electric field? V per micrometer. So, in short channel device, as your length you are already decreasing, so your electric field gets stronger at a lower VDS, getting my point. So, in long channel device, your saturation, velocity saturation was happening above VOV, overdrive voltage, but as in short channel device your length is reduced. So, your electric field is stronger even at smaller voltage. Okay. So, in case of short channel device, this flattening of the current is happening at lower voltage than the overdrive voltage. That voltage is termed as VD sat, and VD sat generally for longer channel device we discussed that VD sat is equal to VGS minus VT, but that value drops to a lower value in case of short channel devices. Okay. So, this effect is known as the velocity saturation effect. In velocity versus electric field, our mobility is constant, but as our electric fields go strong, our velocity becomes constant and this mobility slope they drops. Clear? Because of this constant velocity, what happens? Our current cannot follow the linear relationship, it drops and tends to saturate quite early. This effect is known as the velocity saturation effect. So, you can understand that this VGS minus VT that we used in our longer channel devices, right. So, that will be modified. Okay. So, in this case the current expression is modeled by the VD sat. VD sat is a lower value than the overdrive, this is VOV. So, VD sat is a lower value than the overdrive voltage, and the current expression is modeled by K VD sat. So, we get actually lower value of current. If you see the maximum current, in case of short channel effect our I max is lower than the corresponding longer channel device. So, we have discussed few second order effects starting from backgate effect, channel length modulation effect, and then velocity saturation, subthreshold conduction. Next effect is punch through effect. Suppose your VDS, if you increase your VDS drain voltage, then what happens? That this is a N, right, and your substrate is P, right. So, this is reverse bias, substrate is at ground potential and your drain is at higher potential. If you increase this VDS, what happens? This depletion width is increasing, right, depletion width is increasing. Now, if you keep on increasing these higher values of VDS, what happens similarly, that this depletion of the source region and the drain region, they can come closer and can touch, right. So, if they touch, then what happens, that this electron can just punch through and can cause a large current. Okay. So, this generally this VDS creates an upper limit that you should not go beyond this, so that punch through can destroy your structure. Okay. So, the high value of the drain voltage, the source and drain regions can be shorted together and normal transistor operation stops. This sharp increase in current result from this effect, this is known as the punch through, and this may cause the permanent damage of the structure, okay, and this should be avoided. So, generally this punch through, they sets an upper limit for the drain voltage. Okay. So, the specification, they should provide a specification of the drain voltage that you should not use more than that. So, just like the punch through, in case of punch through, what happens? It is happening due to high VDS. Similarly, if you use high VGS, another effect can happen, that is oxide breakdown, gate oxide breakdown. Okay. As you are using the higher voltage of VDS, the punch through is happening. Similarly, if you use higher values of VGS, this gate oxide can break and can damage the structure. Also, your parameters can change. At high gate source voltage, the gate oxide breaks down irreversibly, damaging the transistor. Next effect is DIBL, drain induced barrier lowering. So, what happens in this effect is that if you use higher value of drain voltage, so this drain voltage is actually helps to reduce the threshold voltage, right. So, if you recall our initial formation of this backgate effect, that when I am applying a positive voltage of VGS, what is happening? It will repel the all the holes beneath the gate, right. If you add a positive gate voltage, this will repel all the holes in the channel, right. So, what will happen? Some space charge region will be formed, right. So, this is the first step. Now, you think in addition to VG, I am also applying a positive drain voltage. Okay. So, this drain voltage will also helps to form this depletion region, right. So, you can think that this drain voltage is taking a burden of the gate voltage, right. So, as if the barrier that what was our barrier? Threshold, right. Threshold voltage was our barrier. Above threshold voltage, our channel was starting to invert, right. So, if you have a higher values of VD, that will actually help to reduce the threshold voltage. So, that is the term drain induced barrier lowering. So, the drain voltage is actually helping to reduce the threshold voltage. So, if threshold voltage is reduced, what will happen? Your current will be more, right, is not it. So, you see this one, the lowest one is VD is 0.1 volt. second one is V d is equal to 2.7 volt, third one is V d is equal to 4 volt, right. Now, you see compared to this lower V d, if I use a higher V d, my current is more. All other expressions are same, VGS are remaining same. So, just this difference in current is happening because of the drain voltage. So, why this is happening? Because the drain voltage is helping to reduce the barrier. What is that barrier? Threshold voltage. Okay. So, your expression, what is your expression? I is proportional to VGS minus VT or VGS minus VT is whole square, right. So, if your this VT goes down, your ID goes up, and that is happening here, right. So, this effect is known as the drain induced barrier lowering. So, this larger drain voltage helps to deplete the region beneath the gate, and hence as the region is already depleted by the source voltage and drain voltage or drain voltage. So, a smaller threshold voltage is sufficient to invert the channel. That is why the threshold voltage is actually reduced in case of larger drain voltage. So, this is known as the drain induced barrier lowering. Now, if you increase the drain voltage sufficiently even higher, then what may happen? It may create a punch through and can destroy the structure. Okay. Now, here you see when your gate voltage is less than 0, there is another effect that is called GIDL, okay. That is gate induced drain leakage. When your gate voltage is positive and less than or near about threshold voltage, then DIBL effect is happening, right. When gate voltage is negative, another effect is happening, that is called the gate induced drain leakage. In that case also you see that drain current is more. Okay. What is the reason for this? In case of negative gate voltage, what happens in the overlap region between the gate and drain, okay, band to band tunneling is happening, and some current, this electron goes through this tunnel and cause a increase in the drain current, as well as the leakage current is also increased in case of this. Okay. So, what happens that your this bending, because of this bending, these electrons can just tunnel through this. Okay. This is like a band to band tunneling. Okay. So, in case of lower gate voltage, there is a overlap region, they goes into deep depletion region, and that causes this current. Okay. And there are few leakage current will also increase from the substrate and the gate current, and the substrate leakage current will also increase because of this GIDL effect. So, in case of GIDL effects, your standby power or leakage power as well as the heat dissipations can go up. How you can improve this effect? If you use graded or lightly doped drain region, so specific structure is there, that structure you can use to overcome this effect. Next effect is hot carrier effect. So, in case of hot carrier, this high electric field, because we are talking about the short channel devices, right. So, in short channel device your length is already short. So, a higher drain voltage will create a higher electric field, and because of this higher electric field, the electron can be accelerated. Okay. They can be very much accelerated, and they are termed as hot carriers, and they collide with the silicon structure. Okay. So, they come up in accelerated velocity, and with the collision they can generate more electron hole pairs. Okay. So, because of this additional generation of electron hole pairs, your drain current will increase, and for long term also this can creates a drift of drain current. Suppose your MOSFET which was showing a specified current, but if you keep on use it for longer time, so you will be seeing some drift in the current, and that drift happens because of this hot carrier effects. And sometimes if this is enough accelerated, this can go and get trapped in the oxide region also. Okay. So, these electrons can go and get trapped in the oxide region also, and thus it can change the threshold voltage, it can modify the threshold voltage. What was your original threshold voltage, that could be little bit changed. Okay. And it can also goes out of the gate terminal, introducing a gate current. Okay. So, because of this hot carrier effect, your IDSAT, GM and VTH they can modify, and these traps it can cause change in the transconductance, threshold voltage and the current. So, this solid line you see, this is a new MOSFET, and this dashed line is degraded. This shows the effect of the hot carrier effect. Now, these are some modified structure which generally are used. So, whatever we discussed as a structure, that is the simplistic structure to understand the operation of the MOSFET, but modern device they use several modifications for better or improved performances and to overcome several of these second order effects in the short channel devices. So, for example, there are some spacer, there are some halo region, some this extension of the source and drain region, that is termed as HDE. So, these different modifications are used for better performances. Okay. So, this is advanced device structure which are used to overcome certain short channel effects. Okay. Sometimes also we use apart from the source and drain region, generally they are having higher polarities, right, higher doping, and in addition to that we can use a graded doping, or we can cover this with a lightly doped region. Okay. So, these are several modifications that is generally used to overcome these second order effects. Now, sometimes this thin oxide layer, this can create a breakdown. So, we can use a high dielectric constant material, so that it oxide thickness is more. Okay. So, this silicon dioxide gate dielectric they are having smaller thickness, right. So, nowadays we are having high K dielectric material like hafnium to replace this silicon dioxide. Okay. And they are having some nickel structure, nickel silicide, and they are having more thickness. So, this can improve the gate leakage. So, high K material, high K dielectric material is used, so that thickness is improved and we can improve the gate leakage current. If you have smaller threshold TOX, your leakage is more. Okay. So, these are some technology parameters, so that we have discussed. So, all of these are used to model your NMOS and PMOS devices. So, in SPICE we have several parameters, right. So, for example, threshold voltage at the 0 VSB, what is that, what is your gamma, gamma is your backgate effect, which level you are, okay, what is your substrate doping, what is your TOX. So, all of these parameters are generally given and that are used. The value of gamma, value of VDSAT in case you are using a in case the device is using a saturation model, okay, what is your mu n COX, what is your lambda, all are specified. We discussed about the process corner, right. So, what is our process corner? We typically we said that generally typical, fast and slow, these three are our basic corners. Okay. So, in case of fast, what happens, our current is more, right. So, here you see current is 37% more. In case of slow, our current is minus 30% roughly. Okay. So, what happens, actually your mobility, right. So, in this case our mobility is more, which creates more current, right. So, now if we have our wafer, we can have different combinations, right. So, suppose we are measuring the performance of the different ICs at different locations of the wafer and plotting this speed of the PMOS and speed of the NMOS, right. So, this corner you see, this is the fast NMOS. So, this corner is fast PMOS as well as fast NMOS, is not it? This corner, this is your NMOS is also fast, PMOS is also fast. So, this corner is known as the fast, right. So, in previous case we said 3 corners, but in this case we will be having 6. Okay. So, you can have fast NMOS, fast PMOS, fast NMOS, slow PMOS, right, slow NMOS, fast PMOS. So, that kind of different models, different corners you can have, clear. So, for example, this is your NMOS is also slow, PMOS is also slow. So, this is your SS corner. Okay. So, if you want to suppose all these boundaries they pass your device specifications, then this is your acceptable, all of these are acceptable. For example, suppose if your performance is here, then your speed is not satisfying. So, the chips that is falling in this region, that is not acceptable, they will be considered as not working. Okay. They fail to pass the specifications, right. So, if you want to check your performance, generally when you do in your lab, when you are doing the simulation, you generally do simulation at only one corner, you are not changing the corner, you are not changing the technology, you are changing your technology process is at typical. Okay. So, whatever the values of VTH, whatever the values of mu n, they will take the typical values. So, but if you go for fabrications, you do not know what will be your mobility, right, what is your VTH you do not know. So, suppose you have designed and cross checked your design for this corner only, and after fabrication you found that your mobility is quite fast. Fast means higher value, if mu n is higher, ID will be also higher, or suppose your mu n is less, so ID will be also less, right. So, accordingly your performance will vary, right. So, generally we discussed this last day also few in few earlier class, that we generally check process, voltage and temperature, all of these corners you need to check. So, when you do simulation, if you check your log file, you will be seeing that temperature is set to room temperature 27 degree or 25 degree, that temperature also you can change, and if you change the temperature, what will happen? Your result will vary. There is an option to change your temperature also. What you are doing? You are using 1.8 volt, right? 180 nanometer you are using na in laboratory. So, you are using 1.8 volt, but suppose you are having a battery operated device and battery is discharged. So, what will happen? This voltage will drop. So, suppose it drops to 1.6 volt and you are having a slow region. It is slow means current is less, your voltage drops, it will also drop the current. So, this goes to extreme corner, right, because of slow current is already slow, less, because of voltage drop it will also affect. So, your performance will be worst at slow and VDD at minus delta. Similarly, temperature, suppose you are at first corner, current is already more. So, what will happen if your current is more? Performance will be faster, but it will burn more power. In addition to this, suppose your voltage because of some fluctuation it is at 2 volt. So, higher VDD, first corner, and suppose temperature also rise, again you will burn more power. So, this kind of all the corners you generally when you do simulation for the final design, you need to check all the extreme corners, at least your design should be working at the extreme corner, worst possible and maximum possible. Next is MOS capacitances. MOS capacitance is important to discuss because that is actually will give our load. What is our load? That we will get the hints from this capacitance model. So, if you recall that whenever you are drawing any digital circuit, you will be seeing some this kind of circuit is drawn. Okay. So, this CL, some will come from this driver itself. So, it is called C intrinsic, right, because of the self, this because of this logic gate, it has also some capacitance. For example, this in case of inverter, what is your common output terminal? Drain, right? Both the drain are connected, drain is your output terminal. So, whatever the CDB, CSB, they will form the drain cap. Okay. Then this wire will also have some capacitance. The next gate, suppose you are driving another inverter. So, whatever the input side cap, that will also come here. So, this is known as the C extrinsic, this is C intrinsic, this is the C extrinsic. So, what is at the input side? Input side means gate to source, gate to drain of the PMOS, gate to drain of the NMOS and gate to source of the PMOS. So, this capacitance of the next stage, they will also come as a load cap. So, all of these at parallel, they will form this CL. Agree? So, that is why it is important to learn the different capacitance model. So, let us start with this structure. So, from gate to drain there is overlap, right. So, this may form gate to drain capacitance and gate to source capacitance, right. Similarly, drain junction to the substrate. So, substrate is known as the bulk, right. So, drain to bulk and source to bulk, they are this junction capacitance. Okay. So, gate capacitance is CGS and CGD, okay, and DB, CDB and CSB, they are the junction capacitance. So, that you can form here this structure. Okay. Now, in this structure if you see this C1 is between the gate and the channel, that is the oxide capacitance. So, C1 is equal to actually because of the oxide capacitance COX, right. C2 is the, you remember that they because of the space charge region that is forming, right, additional space charge region. So, C2 is forming because of the space charge region. C3 and C4 they are forming why? This drain supposed to form from here, right, but there is a little bit overlap. So, C3 and C4 they are actually overlap capacitance, right. So, C3 and C4 they are overlap capacitance. Okay. So, if we consider the CGS will be having two component, one is CGS due to the channel and another is CGS due to the overlap. So, overlap is always small, right, overlap length is very small LD and comparatively channel length is larger L, right. So, in these two component this is bigger, right, overlap is always smaller, right. Okay. So, let us go to the drain to bulk and source to bulk. So, if we draw this 3D view, this is just like a tub, right. This is source junction and if you enlarge it, this is your W, right. So, this is your W and this is your say source region, right. Now, this side is your channel is having electron. So, when we are having a structure, we can have from the bottom to the substrate, we can have one cap, this is known as the bottom wall, right. Another I can have from the perimeter, right. So, this is acting as one plate and the bulk is acting as another plate, right. So, we can this total CDB or CSB, they are having two component, one is bottom wall, another is side wall, right. In side wall you see how many side wall we will consider, this wall and this wall. This side we will not consider because this side is within the channel, in channel there is already electron, na? So, this side no capacitance is forming, clear. So, C bottom is the junction capacitance multiplied by area. Okay. So, this coefficient is given capacitance per micrometer square. So, if you multiply this with your W into L, what is this? This L is actually LS, length of this source region or drain region, W remains same, then you get total bottom plate. And side wall, this parameter is given by femtofarad per micrometer, this is given as femtofarad per micrometer square, but this CJSW this is given as femtofarad per micrometer. So, if you multiply it with the perimeter, then you will get the total side wall capacitance. So, how much perimeter you will get? 2 LS and 1 W. This side we will not consider because this side we are having channel. So, this side no capacitance is forming. Okay. So, the bottom plate is Cj into Ls into W plus side wall is this coefficient, it will be given. I show you na parameters, all the parameters. So, this is given. So, only if your Ls is varying, your total capacitance will vary, and that way it will do. Clear? So, this is known as your junction cap or depletion cap. Next is gate oxide. Now, tell me, suppose you are in linear region, okay? You are in linear region. In linear region, a channel is already formed, right? Inversion layer will be formed. So, this inversion layer is uniform, right? In the source region and drain region, it is uniform. So, this is in your linear region. When you are going to saturation region, your drain voltage is starting to increase, right? And as drain voltage is starting to increase, the channel start to get tapered, right? And it may end early than the drain region, right. So, this is your source, this is your drain, this is your oxide, this is your gate. So, this is your saturation region. So, you see, in case of linear region, your CGS and CGD, whatever the gate oxide in linear region, what we consider that it is equally distributed between source and drain. So, what is your total gate oxide capacitance? COX into WL. So, if it is equally divided, suppose it is equally divided between CGS and CGD. So, half will go to the CGS, half will go to the CGD. That is not happening, we are considering it for the ease of description, right. Total capacitance is COX into WL, right. We are considering that half of the weight is at the source side, half of the weightage is at the drain side. So, you see, in linear region, my CGS and CGD, they are equal and their values are half WL COX. So, this is our linear region, my CGS and CGD, they are equal, right. Now, you think of saturation region. Saturation region, suddenly this channel ends here. So, the CGD, it goes to 0. Okay. So, now you can think that total capacitance was WL into COX. Okay. So, in this case, we are considering that 2/3 of this weightage is coming to CGS, because source side still the channel is there, but at drain side there is no channel. So, we are considering the effect of the gate capacitance is more on the source side. So, you see, during saturation region my source capacitance that jumps, but drain capacitance that remain the same. Okay. Ideally it is 0, but if there is a little bit overlap, that will form a overlap capacitance, that will be having C overlap into W into overlap region, that is LD, that small distance. Okay. If this is your overlap, so this is your LD, this is your L, this is your L, but overlap is this portion. Okay. So, the capacitance formed due to overlap will be also small. So, when the capacitance is off, okay, between channel there is nothing, then the at saturation region the more weightage is on the source side is CGS, 2/3 WL COX. This W into COV, that we will add on the source side also, drain side also, if we consider a symmetrical overlap. Now, at linear region, both of them they comes to same value. Saturation region, source side is having higher cap value, drain side it is having lower value. Now, I am getting into linear region, both of them are having same cap value. Okay. So, as this is drawn from the Vx point of view, So, in this case linear region is coming early, in this plot saturation region is coming early, but values are same. Okay. At triode region the value of CGS and CGD are same. So, what you can recall that your total capacitance is WLCOX, right. So, when it turns on at saturation region, your capacitance first drops. This is where the inversion is happening. Then it enters in linear region, then it is equally distributed to half COX and half COX to the drain side and source side. So, again the total capacitance goes to WL into COX. So, in case of saturation what is your weightage? Not total WL COX, right, it is 2/3 of WL COX. So, that drop is that drop, okay, because the inversion layer is happening. So, this is how the total capacitance is formed. In case of saturation it is more on the source side, drain side it is not there. In case of linear it is equally distributed. In case of off it is only overlap capacitance. Okay. So, we will continue after this in next class.